Easy, publicly strange.
Okay, can everyone hear me?
Yes, sir.
Okay, good. Let's wait for a minute and then we will start. Okay, uh, welcome everyone. Uh, so this is the second week of instructor session. Today we will be discussing about determinants uh, and Cramer's rule, which you will get to know what it is. So before uh, going into today's content, let's start with recalling what you saw last week. Okay. So last week, in my session, we discussed about vectors in R2, how to visualize that, and then vectors in Rn also. All right. And then uh, this is how, and there were two types of vector that we are interested in, which were coming from our set of data. So vectors are of this type. This is a general representation of a vector Rn. And in case of R2, it is this is a vector and this is a vector in R. All right, then we saw that uh, an arrangement of data in an array uh, in terms of row and columns correspond to give you a new uh, object in mathematics, which is called the matrix. Okay, so So a matrix is an array of data of numbers in rows and columns. For example, this is an example of a matrix, the order of which is 2 cross 2. Uh, this is a matrix, let's say A1 up to AN. So the order of this is going to be n cross 1. And this is an array of order
Sir, you are
1
not
cross.
audible.
I'm not audible?
You are, sir. You are.
You are completely audible, sir.
Yeah. I'm audible. Yes. Thanks. Um, all right. So we discussed about matrices. Okay. And in matrix, we have order is represented in this form, where the first entry correspond to the number of rows, the second entry correspond to number of
Sir, your mic
columns.
is turned off.
Who is this guy? Just wait a second.
All good, sir.
Yeah, I know, but let me put a general announcement.
Hello, sir.
Yes.
Can I ask a general doubt, sir? Sir,
Yeah.
can you please share at least one session because this timing is very difficult to join, and some
Sorry.
stats and some stats courses are clashing with the time.
Can you repeat
It's
your
only on
doubt?
Saturday. It's only on Saturday.
Sir, I think he's, telling about the sessions which are overlapping.
Yes,
So,
sir.
Sessions which are on Saturday.
Like,
yeah.
sir, every math session is from 8 to 10 p.m. at the night, so it is difficult to attend daily, sir. So, can some session are in the morning or in the evening or in the afternoon maybe possible?
Yes, and also the TA sessions that are on Tuesday and Friday, I guess, those are clashing with the GNAI courses.
And it is also clashing with the stats two courses, sir.
At least the TA sessions could be like done in the afternoon or day.
Okay. Okay. So
What's GNA?
I'm noted.
What's GNA?
I have noted your
What's GNA?
concern. So basically, what you guys want, let me summarize it. So your TA sessions on which are on Tuesday and Friday, they are clashing with your Gen AI course, right? And the second thing is that you want some of the session to be shifted to be in the morning or in the afternoon, right? These are the two
Yes,
concerns. Okay.
yes,
Okay.
sir. Please.
I will forward your concern to the respective authority. So here is the point. So these schedules are fixed very tightly. Okay. So there is very little margin of changing the schedule. But so I'm not sure whether it is going to be possible. But let me uh, let me pass your concern to the respective
But when it
authorities.
will
Okay,
change, the
who
So there are
manage the
productivity will increase,
other
sir.
classes as
But
well. Like
when the
Thursday
time
is
will
clashing
change,
with
the productivity will
MLF,
increase.
and Saturday is clashing with tools in data science, right? So everything there is a clash, right? I mean, say like
Yeah,
they spoke about
so
the other.
what happens, because these courses are designed for general audience, okay, and then there are people who work in daytime, so they don't have time in the day during day. So for those, it has been shifted. The courses is being taught in the night when everyone is comfortable. So and then, but there are 7 days only. All right, and then you need to conduct PA sessions also, and then
Right,
face-to-face
right.
sessions. So
Yeah,
it is
difficult.
quite
We understand,
difficult
sir.
to manage all these
Yeah.
things. But anyway, I will pass your message to the respective authority who prepared schedules. But don't I would say, like, don't keep hope that it will change. Okay, so this is very
No, we
tight
understand, sir.
schedule. I understand.
That is
Yeah,
absolutely
yeah,
understandable.
yeah,
It's okay. There are
yeah,
so many
yeah.
courses, so many
Pass on.
things, and time is only that. So
Well,
no
right.
problem. So let us proceed.
Yeah, thanks. Okay. Um, yeah, so last time we saw, yes.
So actually, we are not able to add the course calendar for statistics too, and because of that, the 2 days
To
essay.
do that, open your Google Calendar, click on three horizontal lines. Then on your course email, official email ID, you can sync all your chosen courses.
Yes,
I
sir.
was also
I
not able
did
to
that.
do so.
But it is saying that you do not have access to that statistics to calendar,
Madam, why don't
and
you check that with the
this is
Then
happening
I
statistics,
think
only
your
for
access has
statistics
been
statistics.
denied.
TAs and instructors?
Hmm.
I mean,
Guys, so let me interrupt here. So if you guys have any question regarding the course, okay, whatever material I'm covering, you can ask that, because this 2 hours of time, let us use it beneficially so that you can also learn something and I can also teach you something. All right. So let's keep our doubt restricted to this course and the content of this course, and let's not go around ask general questions. All right. If you guys have any question regarding the material covered in this course and whatever I've covered, what I'm teaching, if you're not comfortable, so let's raise your hand and ask me that thing. Okay.
right, sir. Correct.
So okay. So let's not ask general questions. If you have general question, you can ask to the respective authorities. Okay, you can discuss it on there is this portal which is I always forget the name, but there is IIT MIME portal. You can put your doubt. Someone will be there to help you out with all these
Request
technical
form.
difficulties. Yeah. Okay, so you know all these things. So it's better to put your request over there. Okay, Sakshi, if you have any doubt about the material, please ask. Otherwise, I would suggest not to. Yeah. Sakshi? All right. Uh, okay, so let's come back to whatever we aim, what should we cover today. All right. So vectors, we saw vectors, and then we also saw matrix. Another way. Yes, Sakshi.
Sorry, sir, my earphone got unplugged. Sorry. Sir,
All
I
right.
am asking some of the student are talking about Gen AI. Is it the part of maths too?
I am not sure about that course. So if you have doubt about this course and material, then it is, please go ahead.
Foundation.
All right.
Okay, thank you, sir.
Okay. Uh, right. So we saw matrices. So can anyone tell me? So you can write. So I will ask questions. So you can write your answer in the chat box. Okay. You don't need to unmute yourself and answer why. So it will be easier for me also, and it will be easier for you also. So, all right. So what do we call these metrics? The matrix of this form where it has n rows and only one column.
Column matrix. Sorry for the
Yeah. Yeah.
row matrix.
And what about the other matrix? It is called the row matrix. So, all right. So we saw some of the properties of a matrix also, that they can be added to each other, and then their multiplication, the scalar multiplication of a matrix, and so on and so forth. And then we also talked about the determinant of a matrix. Okay, then we saw some examples of matrix. So what were the examples? So a matrix is called a square matrix if it has number of rows is equal to number of columns, and number of rows is equal to number of columns. And then a square matrix is called a diagonal matrix uh, if it only has diagonal entries. All right. So that means all other entries are zero if I and j are not equal. All right. And then we saw a scalar matrix, which is a diagonal matrix uh, with all I entries to be some same number R and ij entry to be 0 if they are not equal. Okay. And then we also saw identity matrix. So it is a scalar matrix with all I entries to be equal to 1. All right. So this is what we saw in the first live session, and then in the next live session, and we also saw one more thing: how to present a given system of linear equation by a matrix. Okay, we will recall that in the later half of today's session, and then we also talked about the matrices, determinant of a matrix. All right, so let me put this below here. All right, let me shift this a bit up. Good enough. All right, so yes, okay, determinant of a matrix. So, so let's start with this example of 3 cross 3 matrix. So, can anyone tell me what is the minors? What are the minors, let's say, of 1 1 of first entry? What is the minor of first entry? What are the minors of the first row, basically?
-2, 1/2, -2, and -1.
So, minor, what is a minor?
3.
Sir, can you a little bit elaborate on minor and cofactor?
This is covered last week, so I'm revising this.
Oh, sir.
So, does
Okay, sir.
anyone know about minor? What is the minor of 3? This first entry?
It's generally a matrix of no
So,
other than that of a given matrix.
Yes, sir. Can I tell?
yeah,
Hello,
please.
sir. 3.
You can
Right.
remove.
For 3, sir.
3, sir, 3.
Sir,
Is
minor
it
will be
3?
1, sir.
Like minor
All
of
right.
3 is
Determinant of -2, 1/2, -2, and 1.
correct.
Yes. Okay, correct. So that is correct answer. So minor is 3. Someone has already said it. And how do we calculate minor? So for if I want to calculate minor of this entry, which is 1 comma 1 entry, then I will remove the respective column, the first column and the first row. All right. And I will get a submatrix, which is again a square matrix of 2 cross 2 order. All right. So minor of 3. So minor of so minor is denoted by M11. Okay, this is the notation for minor. So minor of this is precisely the determinant of the submatrix after removing the rows, first row and first column. All right. So this will be the thing, and the answer to this determinant of this is nothing but it is 3. All right. Now, what is the minor of 1 comma 2?
-4.
-4.
Minus
-4.
minus 4. Right. It is minus 4 because we will remove which row we will remove because you want to first and second entry. So we will remove the first, we will remove the first row and second column. All right, first row and second column. So what is the remaining submatrix? It is 4, 0, half, -1. And what will be the determinant of this? It is -4. So it is
-4.
answer is minus. Right. All right. Now, all right. Now, and what is 1 comma 3? So what is the minor of 1
-8.
comma 3? It is going to be
-8.
-8.
-8.
-8.
Right. Right. Now, can anyone tell me what is the cofactor? So,
Minus
cofactor.
It's
power
minus 1 to
I.
the
minus
power
1
I plus j,
sir,
into which
I
minus.
plus j.
Okay, so you are telling me the general form. So cofactor of ijth entry is minus 1 to the power I plus j times the minor at ij, right?
Yes, sir.
So now what is C11? What is the cofactor at 1, 1?
So it's same as its minus
Minus 1 to the power 2.
Same, sir. 3.
3, sir. 3 will be 3.
Yes. What about 1, comma 2?
Uh,
4.
Q.
4.
4.
Right. What about 1, comma 3? Which will be
Minus 8.
wait, wait.
Minus 8.
right. Right. So the formula. So given an n cross n matrix, let me write that down. Right. So given an m cross n matrix, let's say, let's say A is an m cross n matrix, A11, A12 up to A1n, A21 up to AM1, A22, A2n, AMN. It is an m cross n matrix. All right. So given an m cross n matrix, uh, yeah. So in order to find out determinant, in order to find out minor and cofactor, we need to work with square matrix. So I cannot work with, so this will only make sense when I have m equal to n. All right, so let me take it to be n cross. Now it is an n square matrix n cross n. All right. So now what is a minor ij of ijth entry? It is determinant of the matrix after removing the ith row and jth column. Okay. So I will denote. So let me write it in bold. So determinant of some matrix obtained from A after removing ith row and jth column. All right. And what is the cofactor? Cofactor is this factor of -1 times the minor. All right. Now we can use minor
Sir,
and cofactor.
sir,
Yeah.
like this rule minus 1 to the power I plus j. Sir, this is the same when we calculate determinant. So we use this thing in
Yes.
assigning signs.
Yes. Yes. We use this.
Okay.
Yeah. So this is what I was about to tell. So determinant of A. Now, if you want to express determinant of A, you need to expand your determinant. You need to multiply cofactors of one row. You need to fix a row or a column, and you expand along that. All right. So let's say if I expand along this first row, then I will be looking at the columns. Then I will looking at the cofactors uh, of the first row. So in particular, so if I expand along the first row, let's say, so I will be looking at A1j times the cofactor Cj. Okay, and j will vary from 1 to n. And now this is same as expressing it in terms of minor uh, by writing the expression of cofactor in terms of n. All right. So here I is 1, C1j. So it means that I'm expanding. So this is determinant. So this is determinant expanded determinant of A, expansion along row 1. All right. Now you can do that with respect to any row and you will get the same determinant. All right. So in particular, you don't need to expand along the first row. You can expand along any row or any column. All right. So let's say expansion along row I. All right. Some row I. So what will it will give you? So how will I do that? So Aij. So I is fixed in this case, and j will be varying. And then you will look at the cofactors in that row. All right, and j will vary from 1 to n, which will again be same as Aij minus 1 I plus j m I j. All right. Or you can have expansion along some column along column j, and in this case you will have vary I. All right. So determinant of A will be Aij Cij. Now j is fixed. In this case, j is fixed, so you will vary I. Now this is again same as in terms of matrix. This is just matter of. So this is what it is, and you will get determinant to be same. So in particular, determinant of A is independent of the choice of row or columns used to calculate it. All right. So whichever row you take, whichever column you take, you will get the same number as determinant of a matrix. All right. So let's take an example of it to have a better understanding what I'm trying to say over here. So let me use another image. Okay. All right. So now let's say uh, so this is some. Okay. So now let's take determinant of this. Okay. So now let's find out determinant of B along by expanding. So determinant of B first by expanding along row 1 along row 4. Okay. So let's do that. So if you do that, so what are the cofactors in that? So cofactors will be C1, sorry, C41, C42, C4. Okay, so let me write down the formula first. So determinant of B would be A41, C41, A42, C42, A43, C43 plus A44, C43. All right. Now, if you now what are A44, A42, A43? So these are values. These all three values are 0. All
Zeros
right.
and minus 1.
These, right? It will be 0. So these three terms. So you don't need to calculate these cofactors because their coefficients are 0. So what it will be? It will be just equal to A44 C4. Now what is A44 C44? It is minus 1. All right. And then minus 1 to the power I plus 4 plus 4 times M44. Right. Now what is M44? M44 is the determinant after removing this row, fourth row, and fourth column. Okay, fourth row and fourth row and fourth column. So this matrix, determinant of this matrix. All right. So now what is the determinant of this matrix? It is 1, 2, minus 3, 2, half, 1, 0, 0, 2. Okay. So what is the determinant of this? Again,
7/2.
you can find, again you can find out determinant of this by expanding along the third row, because in the third row, you see there are two factors which are 0, so it will correspond to, so you don't need to calculate the cofactors corresponding to them. You only need to calculate the cofactor corresponding to this non-zero entry. So again, so it will be just determinant of this times 2. So it is 2 times determinant of 1, 2, 2 half. All right. So now what it is? It is 2. It is half minus 4. Half minus 4, which is going to be 7/2, right? Minus 7/2. So it is minus 7. So the answer here will be minus 7. So determinant of B is also minus 7.
Sir,
Now,
we
if you
understand
expand,
determinant, sir, 1 second. We understand determinant, but what is determinant along row 4? I mean, is this a difference?
no, it is same. I'm saying I'm finding out the determinant by expanding along row 4. That is what it means.
Okay.
Do you
I
understand
think
what I'm trying
overall
to say here?
answer is 7.
Yeah, overall answer is 7. That is what we have find out. It is 7. Now, what I'm showing is that it doesn't matter which row you choose. Okay, to find out your determinant. You can use row 4. Row 4 in this case, it's simple because you have three factors are 0. So only need to calculate cofactor of one element. Okay, there is only one non-zero. So now now expand along row 3 and then let's see what you will get. So determinant, now finding determinant of B by expanding along row 3. So along row 3 means determinant of B is given by this expression C31, sorry, A31, C31, A32, C32, A33, C33, A34, C34. All right. Now what is A31? A31 is A31 is 0. A32 is also 0. And A33 is 2 and A34 is 1. All right. So you will get this is equal to A33, C33 plus A34, C34. Now A33 was 2, C33, A33 was 1. So it is fine. Now what is C33? C33 is 3 plus 3 times the determinant of the minor corresponding to it. So that means since it is C33, so you remove this row and this column. So this is the remaining matrix. Okay. So remaining matrix is 1, 2, you have 0, 0 over here, minus 1 over here, 2, minus 1. Okay. If you calculate the determinant of this, you will again get 7. All right. Now what is 3C, 334? It is minus 1. Determinant of 3, 4 entry, which is this. Removing this row, this column, and this row. So we'll get this matrix? Oh, sorry. Yeah, there it will be 7 by 2. Yeah. It is minus 7. No, it will be plus 7. So it is basically minus 1 times half minus 4. So which will give you 8 minus 7 by 2. Yes, so it will be plus 7. It's plus
Sir,
7.
minus 1 to the power 6, so it would be plus 1. Then,
Yeah, that is true. But here it is minus 1, right? This is minus 1. I'm expanding along row 3. So it is minus 1.
okay,
All right.
okay, sir.
Now, yeah. So now if you calculate, now I'm calculating, now what is the cofactor of 1, 1? It is fourth column and third row. Okay. So cofactor of 3, comma 4 is third row, removing third row and fourth column. So you will get 1, 2, minus 3, 2, half 0. 2, 1, 2, minus 3. Last row is 0, 0, 0. And 2, half and 1. 2, half, 1. All right. So later you will see that if a matrix has a 0 row, so this is one of the property of determinant. If the matrix has a 0 row, then the determinant of this of that matrix is going to be 0. So this is 0. Okay. So what will be the answer? So answer is determinant of B expanding along the row 3 it is 7 by 2, 2 times plus 0, which is 7. So it is 7 here. It should be 7 over here also. So there must be some computational mistake. Yeah, there it was. Yeah, it was coming out to be 7 minus 7. Right. It was coming out to minus 7, and here there was factor of minus 1. So it should be 7. All right. So as you can see that, let me zoom out. So as you can see that determinant of B expanding along row 4 is minus 7, and determinant of B expanding along row 3 is again, sorry, determinant of B expanding along row 4 is 7. All right. And similarly, determinant of B expanding along row 3 is again 7. So it is independent. So it is independent of the choice. It is independent of the row you want to expand. So usually we expand along the row which has lesser number of non-zero entities. For example, so this will help us computationally. So for example, we have expanded, it will be easier to expand along this row because it has 3 zeros and only one non-zero entity. Okay, so it will be easier to expand along. So let us look at some of these kind of properties of determinants. Okay, so one of the first properties is that if you add any multiple, okay, if you add any multiple of row to any other row, so the determinant of that remains unchanged. All right. So for example, let's work out this in this example. So for example, what is the determinant of A in this determinant of this matrix, first matrix?
-1.
It is -1, right? And what is the determinant of B, which I have obtained after performing this row operation? So what is the row operation that I perform? I have changed my R2 to R2 plus 3R1. That means I've added 3 times of R1 to R2. So if you add 3 times of R1 to 3 times of R1 to R2, what you will get? First entry will be 3 minus 3. Okay, so it will give you 0. Second entry will be 1 and 1 minus 0. So 1 minus 0 is 1. So what is the determinant of B? Determinant of B is
-1.
-1. Right. So what you can see here is that addition of a multiple of a row to any row does not change the determinant of the matrix. All right. Now let's do an addition. Now let's add a column some multiple of a column to another column. Okay, and let's see whether does it change the determinant or not. So let's take the same matrix A and then perform a column operation. That means you change C1 to C1 plus twice of C2, or let's say minus thrice of C2. All right. So what will you get? So you will get B, which is of, so second column remain as it is 0, 1, because I have not changed anything to this. Now the first column will be, because minus 1 times 3 times of the second column, so it will be 0. So it will be minus 1 only. Okay, because I have not, what's the second column? Second column is 0, 1. So 3 times 0 is 0 again. Okay, so you are not subtracting anything from the first entry. Now in the second entry, so you are doing 3 minus 3 times 1. All right, so it will give you 0. So this is 0. So what is the matrix? So you get this as the matrix. All right. Now what is the determinant of B? So again, the determinant of B is minus 1. So what you have seen is that determinant of the matrix does not change under, uh, yeah, determinant of the matrix does not change under the addition or yeah, it does not change under addition or multiplication. Okay, so let me write down that property. So adding multiples of a row to another row leaves the determinant unchanged. Okay, okay. So row or column. Okay, so another row leaves another thing. And uh, similarly, I can have the same thing. I can say the same thing for column. All right. Now let's look at this um, matrix A. All right. So now let's look at this matrix. So you can calculate the determinant of this matrix by expanding along any row, or what you can do, you can realize that this row, second row, is addition of the first row and second and third row. All right. So in particular, you can write down this row vector as some multiple, basically twice of the first row and adding the third row. So in particular, R2 row 2 is 2 times row 1 plus 1 times row 3. All right. So what is happening here is that the row 2 is expanded in terms of the addition of the first row and the third row. So that means row 2 can be expressed in terms of row 1 and row 3. So in these cases, when you can express one of the row in terms of other two rows, okay, or one row in terms of just a another or multiple of another row, then in those cases, the determinant is always equal to 0. Okay, so you can directly use this as a computational hack to find out by writing this that row 2, since row 2 is a scalar multiple, it is sum of two rows, so that the determinant of row is going to be 0. Okay, and you can compute also by expanding along any row, and you can check that that is what is happening. All right. So let's do the computational check as well. So let's say expand it along row 3. All right. So if you expand along row 3, what will you get? Is that you only, because the first entry is 0, so you don't need to uh, uh, calculate the cofactor of the first entry. Calculate the cofactor of the second. Let's do that. So it is uh, so determinant of A is equal to particularly -1 times 3 plus 2 minus 1 times the determinant of 1, 2, 0, 1 plus uh, 1 time the determinant of 1, 2, minus 1, minus 3. All right. So it is -1, which is 1 you will get here, and then plus 1 times -3 um, plus 2 it will be 0. All right. So this is another property of the determinant. If two rows, if a row is a linear combination, so this is called a linear combination. You will see this term later also. So this is called this is what we call a row 2 is a linear combination of linear combination of row 1 and row 2, row 3. All right. So in such cases, determinant of A is 0. Is this clear?
Yes, sir.
Okay. Now, so this is another computational easiness. Whenever you have our row to be 0, okay. So as I've already told that whenever you have a row to be 0, in that cases, determinant is always going to be 0. And why is that so? The proof is quite simple. So for example, I have already mentioned that you can expand your determinant along any row. So when you have one row to be 0, you expand along this row. Okay. So this is the usual tendency. Wherever there is most 0, we expand along that row or column to find out the determinant. So we will expand along this row. Now, because all coefficients of cofactors are 0 in that case, so let me write it down. So determinant, so I'm expanding along row 4, so it is A41, C41, A42, C42, A43, C43, A44, C44. All right. Now, all these entries, now all these entries are 0. So we will get 0 times C41 and all this is, so we will get 0. Okay. So determinant of A is 0. Uh, in particular, the property is um, if A has A, which is of n cross n, has a zero row, or a column, or a 0 column, that is all entries in that row or column are zero, then the determinant of A is zero. Okay. So this is quite direct from the definition of the determinant. All right. Now let's look at this property. So what I'm doing, I have a matrix A. I am multiplying it by a scalar multiple. I'm multiplying a row by a scalar. Okay. So I'm multiplying a row by a scalar. All right. In this case, it is 1 by 3. So I will get another matrix P. So let's do that. So if I divide row 1 by 3, what will I get? I will get 1, comma 1, 1, 2. All right. This will be my new matrix. Right. Now, what is determinant of A? So determinant of A is, can anyone tell me what is determinant of A?
1 by 3. 1 by 3.
1 by
1
3?
by 3.
It's minus 3. Sir, it should be 3. Determinant of it.
1 by 3.
Why 1 by 3? Those who are saying 1 by 3, we need to just recalculate the computation. There is no
1, 3. 1 by
rational.
3.
And what is the determinant of B?
1.
1.
1.
Yes, sir, it is 1.
Right? It is 1.
So how did you get B from A?
So I'm getting B from A by substituting my row 1, by dividing my row 1 by 3, by a scalar multiple of 3. 1 by 3. I'm dividing row 1 by 3.
Okay, okay.
Right? So now.
So are you allowed to do that?
Yeah. So I'm changing a matrix. I'm getting a different matrix. Okay. And I'm getting different determinant of. Now I'm going to tell what is the relation. So relation
Okay.
is, so you have divided your row by 1 by 3. All right. So the effect of this operation on the determinant is precisely 1 by 3 of determinant of. Okay. So what is determinant of B? It is 1 by 3 of determinant of A. All right. Because determinant of A was 3, and after operation you obtained matrix B. So determinant of matrix B was 1. B is 1, and which is 1 by 3 of determinant. All right. So what
You
you have
can
noticed
also
is that.
say, I think, take out 3 common out of A.
No, that doesn't make sense, because you can only take out a scalar out of a matrix when it is multiplied to every entry of that matrix. Okay. Otherwise, you cannot take out. All right. So this is what has happened. Now let's do. Now let's multiply column 1. Now replace your column 1 by dividing it by 3. All right. So what will you get? You will get that
1, 3. 1
you
by
will get
3, 2.
right 1 3 1 by 3 2. Correct. Now what is the determinant of this matrix?
Sir, it is 1.
It is 1. Right? It is 1. Again, it is 1 by 3 of determinant of A. Right. So what you have noticed from this computation is that if you multiply your row or column by a scalar, all right, so the determinant of the new matrix is that scalar times the determinant of the original. All right. So in particular, in generality, if you can write it, so suppose A is a matrix, A is an n cross n matrix, and B is obtained by multiplying by multiplying multiplying uh, ith row of A by I scalar k, all right, or jth column by I scalar k, then determinant of B is going to be k times scalar of k times determinant. Right? So this is another property. All right. Now let me write down few more properties of determinant. All right. Now, what are the other properties? Yeah.
Sir, can you show the previous property? The previous one.
This one?
Yes, sir.
Excuse me, sir. Can we think it like this? That can we think it in terms of a visualization of a vector?
Okay.
Sir,
How do you
it's
want to
like
go
a
about it?
scaling
Yeah.
of vectors, which we studied in physics or all these things.
Right. Yes.
So can we think it in terms of visualize in terms of vector basically? So this is what the crux of it.
If you want to think about in terms of basic vectors, then you need to have appropriate setup to think about it. I don't have immediate answer to that question.
So it's like scaling of vector and all these things.
Yeah, I
You have
understand. I understood your point. It is something
yes,
like a scaling. We're doing scaling of a row vector. If you think of
yes,
that, you're
yes,
scaling a
sir.
row vector, right? But determinant is a different operation. It is different object. Okay. It is
Okay.
yeah.
Thank you.
Right. Right. So okay. So now let's write down other properties as well. Yes. So this is one of the crucial property. So determinant of a product is a product of determinants. So what does it mean that
Sir,
if
will
you
you
have
share these
A,
notes?
yeah, if A is n cross n and B is also n cross n matrix, then we have talked about the product of AB because the number of row and number of column of these thing matches. So for any square matrix, you can always talk about product. So the product will be A cross. Okay, so determinant of A cross A times B is nothing but determinant of A times determinant of B. So in other words, determinant is additive. Determinant is uh, yeah. So when you multiply two matrices, determinant of the multiplication of the product is equal to the product of the determinant. All right. Yes, Sahil, do you have any doubt?
So I tried to solve the week one graded assignment, and in that there's a lot of stuff that we have not covered in the week one lectures, like what trace functions, eigenvalues, then like those things are asked, but is not covered in the week one lectures.
Eigenvalues.
Like I've asked a friend who has like done linear algebra, and he said there's like an eigenvalue. I have no idea what that is. Like trace
I
functions,
don't think so.
questions asked based on
I
that.
don't think so. Eigenvalues will be part. Eigenvalue is not part of week one syllabus.
There's
Where
like
did you
trace
find this?
function or something. Like he said that it
Trace
is
can be
related to
defined.
eigenvalue.
Trace can be defined. No, it is not related to
Okay.
Who said that?
Sir, overall the problem
No.
is in week one when we are trying to solve the graded assignment, I believe the TA session we have not covered the assignment part, right? I think Prakhar sir, it was the last class when he was trying to teach the concepts only. So I think this the solving part has to happen, right? I mean, there has to be a session where we check with
That
our.
will take place after the deadline passes, not yet, I guess.
No.
Yeah, assignment cannot be solved before that. Yeah.
Graded assignment.
Activity
Yeah.
questions. So TA sessions are supposed to discuss activity questions.
Sir,
All right,
that has
and you
not
can ask
happened.
questions from practice assignment.
No, that is also pending. That is also pending. That is what I'm trying to highlight.
So activity questions has not been discussed. That is what you are saying?
Yes.
Then what was discussed?
So we were discussing in the last class mostly the concepts where Prakhar sir informed that is his last class. So probably the next year whomsoever will come will take that thing up. So we have some problem on the assignments, not the graded one, but the activity assignments, activity questions actually.
So you are saying it was not discussed. No problem. Activity questions will not be solved. That is what you are saying.
Yes.
None of the activity question was solved.
Yes. As per
Activity
my
and practice assignment questions.
None of that is solved.
TA session only focus on concepts, not problem solving assignments.
Okay, I think from the next time it will be more on discussing activity questions. It was supposed to discuss activity questions, so I will talk to them. All right.
Sure, sir.
Okay.
Thank you very much.
Yeah. Okay, so this is the another property. The product of the determinant is equal to the product of the determinant of a product is equal to the product of the determinant. All right. Now, what is the second property? Second property is that switching to rows or columns changes the sign. Okay. Now, what does it mean? Let me give an example. So, let's say you have a matrix. You have matrix A given by this, and now you switch rows. Okay. So, what you do, you interchange. R2 becomes R1, and R1 becomes R2. All right. So, what is the new matrix? It is basically this. Now, call this matrix to be B. Now, what is the determinant of A? Determinant of A is 4 minus 6 minus 2. What is determinant of B? It is 6 minus 4, which is 2. So what you see? So there is a change in sign. All right. So determinant of A is minus of determinant of B. Okay. So switching two rows or two columns changes the sign. That is what the second property is. You can also work out with more examples. Let's say you change column with A. So you change C2 with C1. You will get 2, 4 and 1, 3 as your new matrix B. Now, again, if you calculate the determinant, it is going to be 6 minus 4. It is going to be again 2. All right. So again, the sign has been changed. All right. So I've discussed 4 properties. I've discussed basically 6 properties computational easiness. So one of them switching of two rows and column changes the sign. Determinant of a product is equal to the product of the determinant. If you multiply any row by a scalar or any column by a scalar, the determinant changes by also that scalar. If if there is a row which has all entries to be 0 or any column which has all entries to be 0, then the determinant is going to be 0. If you can write any of the row or any of the column in terms of other rows, in terms of the linear combination of other rows, then determinant is going to be 0. And you can add any two rows, sorry, adding multiple of a row to any other row or any multiple of a column to any other column does not change the determinant. Okay, so these are the 1, 2, 3, 1, 2, 3, 4, 5, 6, 6 properties that I have discussed with examples. Okay, so now let me again recall what. So we have already seen what are the square matrix. We are dealing with the square matrix only because we are working with determinant of a matrix, and yeah, we are dealing with determinant of the matrix, and so determinant is defined for the square matrices. Now, let us take our study further. So in last session, we have discussed about system of linear equation. Okay, I gave an example of a fruit vendor. Okay, if you guys remember, and we want to find out the price of 1 kg of a particular fruit. Okay, by having some equation, linear equation. So so in generality, we can have a system of linear equation. So let's say I have a system of linear equation given by this. Okay, 3x plus 4y is equal to 12, x plus y is equal to 5. Then we can associate a matrix to this by writing the coefficient of the xy's in a matrix form. Okay, because this is the information, this is the data, and I can encode this data in terms of a matrix. Okay, in terms of an array arranged in row and column. Okay, so the corresponding matrix is called the coefficient matrix. So this is called the coefficient matrix. Matrix. It is clear from the nomenclature why it is called coefficient matrix, because it is taking the coefficient of x and y and forming a matrix. So that's why it is a coefficient matrix. Okay. So let's say A is a coefficient matrix. Okay. So in terms of the coefficient matrix, you can write down your system of linear equation as a product of matrix like this. Okay. So matrix A multiplied with xy, the unknowns, is equal to the column vector, column matrix given by the values on the right hand side. All right. So this is a matrix presentation of a linear system of equation. So this is what we have discussed already last. Now, if you have number of equation equal to number of unknowns, all right. So if you have number of equation, if number of equation is equal to number of unknowns or variables, whatever you want to call them, unknown or variables, then you can notice that the coefficient matrix, then the coefficient matrix is a square matrix. All right, and it will precisely be equal to number of equation or number of variables. So in today's discussion, we are interested with square coefficient matrix. Okay, so now we want to shift our attention to solving these system of equation. Okay, so now throughout this course, you will study various methods to solve a system of equation. In today's discussion, we will look at the Cramer's rule. Okay, we will work with, first of all, a system of equation where the number of equation is equal to number of variable. So the coefficient matrix, associated coefficient matrix, will be square matrix. And so we will be working with these system of equations, and we will see what are the possible ways to solve them. Okay, some of the possible ways to solve. Okay, so this is what it means to solving a system of equation. exactly to find out uh, the all possible values of the unknowns or variables. All right, that is x, y, z, and so on. Okay, whatever the variables you have. Right. Okay. So let's look at Cramer's rule. Okay, so this is what we are going to discuss today. So let's start with Cramer's rule. Let's start with this system of linear equation itself because it is number of equations is 2, number of variables is also 2. So we have a square matrix associated to that. So now let's look at this system of equation only. All right. So in Cramer's rule, we use determinant of the coefficient matrix. All right. So now let's first write down the associated coefficient matrix. It is 3, 4, 1, 1. Now what is the determinant of A? Determinant of A is 3 minus 4, which is minus 3. Yeah. Now in Cramer's rule, what we do, we first write down, we replace this first column with the entries on the right hand side. So that means 12 and 5. Okay. So as I said also, that you can think of this matrix as, you can also think of this linear equation as in terms of the coefficient matrix like this, right? So, so we obtain a new matrix A1 by replacing the first column, okay, by replacing the first column with the entries on the right, with the column vector on the right hand side. So we get this matrix. We call that to be A1. A1 because the matrix is, yeah, so the matrix.
So this is the different
Okay.
matrix.
Yeah, this is a different matrix. Let's call them AX1. Let's stick to the notation that is being used in the so AX1. So I get this matrix AX1. Why AX1? Because I will use this matrix to find out value of X in particular. So let's call it AX. Okay, I will use this matrix to find out the value of X by replacing the first column by the right hand side column vector. Okay, so now look at the determinant of AX. What is the determinant of AX? It is 12 minus 20. It is minus 8. Right? Similarly, I write down matrix AY by replacing the second column with the column vector on the right hand side. So it will give me 3, 1, 12, 5. So what is the determinant of AY? AY is 15 minus 12, which will give you 3. Okay. So what does Cramer's rule says that you can find out values of X and Y by using these determinant values. Okay. How? So in particular, if determinant of A is non-zero, then X is equal to determinant of AX by determinant of A, and Y is equal to determinant of AY divided by determinant of A. All right. So we know what is determinant of AX. Determinant of AX is minus 8. Determinant of A is minus 1. So it will give you 8. So X is 8. What is Y? Y is 3 minus 1. So answer is minus 3. So 8 and minus 3 is the solution to the given system of equation. Now let's verify. So if you write down, okay, so now let's verify to the equation. So let's verify. So if you 3 minus 8 plus 4 times minus 3, it is 24 minus 12, which will give me 12, and minus, sorry, 8 minus 3, it will give me 5. Okay, so it is satisfying the right hand side. All right. So this is the method of Cramer's rule. Okay. But in order to apply Cramer rule, you need to have determinant to be non-zero. Okay. If determinant is not equal to zero, if determinant is equal to zero, then you will have infinitely many solutions, and you cannot use Cramer's rule because in Cramer rule you divide it by determinant. All right. So you cannot divide anything by zero. Okay, that is undefined. So in order to apply Cramer's rule, you need to have determinant to be non-zero. So that is the only condition on the coefficient matrix, and then you can find out the Cramer's rule. Now we are in situation to write down the necessary conditions what we saw. So first of all, we notice that the coefficient matrix is a square matrix. Okay, so that means the number of equation was same as the number of variables. All right, and the second thing we notice that in order to apply Cramer's rule, we work with determinant. We work with non-zero determinant coefficient matrix. All right, so this is the second condition. So we are working with square matrices. That means we are working with the system of equation which has number of equation to be equal to number of variables, and their corresponding coefficient matrix has determinant to be non-zero.
Sir, can you repeat AX and AY again?
Yeah, I will come back to that. Yeah. So in particular, we are studying in today's session, we will discuss linear system equations with coefficient matrix with non-zero determinant. All right.
And sir, for
now
that, how do we see that whether it has a unique solution or many unique many solutions kind of a thing? Because those are the things are there in the question actually.
Yeah. So if it has a unique solution, yeah.
Yes, sir. Go on.
Right. So So right. So in Cramer's rule, if you are working with a system of linear equation which has number of equation to be equal to number of variables, and the determinant is non-zero. So in that case, if determinant is non-zero, then it has unique solution. If determinant is equal to zero, then it has infinitely many solutions. Okay. Now let's look at Cramer's rule for 2x2 matrix. Okay. So first of all, you will have some system of linear equation A1 x plus x1 A12 x2 A21 x1 plus A22 x2 is equal to some B1 equal to B2. So this will correspond to a coefficient matrix A, which is of this form A1212, A21, A22. All right. And then your variables column vector will be x1, x2, and your value column vector will be V1, V2. All right. Now, if a determinant of A, so this is your A, is non-zero, then Cramer's rules tell that. Okay, so yeah, if determinant of A is non-zero, then you define AX1, which is by replacing the first column with the column vector on the right hand side. All right, and finding out determinant. Okay, and AX2 by replacing it with the stacking column. All right, and then x1 is equal to determinant of AX1 divided by determinant of A. X2 is equal to determinant of AX2 divided by determinant of A. All right. Now let me write down the general expression for n cross n matrix. Suppose you have n equations and n variables. A11 x1, A12 x2, dot dot up to A1n xn is equal to B1, A21 x1, A22 x2 up to A2n xn n equal to b2. And like that, you have n many equations. Let me write down the last n equation. All right. Now, what is the corresponding coefficient matrix? A, it will look like A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN, all right, multiplied with the unknown variable matrix, variable column vector, and equating it to B1, B2 to Bn. So this is my AX, this is X vector, and this is B vector. Understand? So again, if determinant of A is non-zero, I define AXI so AXI is defined to be matrix obtained from A after removing ith column by this vector. All right. And then AXI is equal to determinant of AX. XI, determinant of XI, sorry, value of XI is equal to determinant of AXI divided by determinant of. All right. For pi varying from 1 to 10, we have this. All right. This makes sense, right? Um,
Sir, what is bar and ax bar equals to b bar? Have you put there?
yeah. So AX bar, I'm denoting X bar by this vector, I'm denoting by X bar, and this vector I'm denoting by B. All right.
Okay, sir, got it.
Yeah. Any other
Uh,
questions?
yes, sir. So I have a
Yeah.
question, sir. Why didn't you put this bar over A and you have put it only over X and B?
Yeah, because I've already defined A to be a matrix, and I'm giving A to be this name. The matrix is named A, and I'm naming small x because small x I've also used as variable. So in order to distinguish from it is not a variable x, it is
Okay.
different quantity and a variable that I'm putting bar over.
Yes, sir.
Okay,
Got
because
it, sir.
these
Thank you.
small letters I use as scalar also. So I just want to distinguish them.
Yes, sir. Yes, sir. Thank you,
Right?
sir.
Okay. Any other doubt? If
Sir,
not,
how,
then we
sir,
can move ahead. Yeah.
how do we get the equation xi is equal to determinant of axi upon determinant of a from the matrix equation? Ax bar is equal to b bar.
You want me to prove this? It is out of your syllabus, so I don't think we should discuss that. You are asking me how do I get this, right?
Yes, yes,
How do I get it?
yes.
Yeah, at least you want me to prove that. That is out of scope of this thing. But if you're interested, you can look at. I think Wikipedia discusses it in somewhat detail. We
Okay,
can
sir.
have a look at over there. And if you still have some question regarding the proof, we can discuss it sometime. If we find some time
Okay,
for after live session, then we can discuss it. All right, but it is not part of the syllabus, so you guys don't need to look at the proof. You just need to know how does this work. Okay.
Sir, just
All right.
one more question
Yeah.
here. Of course, I have missed the initial part of the class. I hope my question is not out of syllabus kind. Sir, you have written AXI equal to matrix obtained from A after removing ith column by.
Oh, After
So is
replacing,
it replacing?
okay.
Is it replacing or
Yeah, it's
removing?
replacing. Sorry, sorry. Yeah,
Yeah,
it's
yeah.
replacing. Sorry. Thanks for pointing it out. Yeah, it is replacing. It is replacing. Uh, thanks. Yeah. All right. Okay. So now, so we have discussed one type of solution by using the Cramer's method. And for that, what were the requirement? We work with the square matrix, and the determinant of the matrix should be, coefficient matrix should be non-zero. Then we can have the Cramer's rule to find out the solution. Now, so so when we have this condition on a system of equation, then we know that you can write your system of equation by this: ax bar equal to by, where A is an n cross n matrix, X is n cross 1 matrix, B is also n cross 1 matrix. All right. Now, if you know the inverse of a matrix A, if you know the inverse of a matrix of A, so that inverse has already been discussed, I think, in the week one. So if you know the inverse of the matrix, what you can do, you can multiply inverse both sides of this equation. All right. And so I'm multiplying from the left. Okay, so it matters where do you multiply it. It is not, it is unlike the real numbers. So it matters if you multiply your matrix by left or multiply your matrix by right. So what do I mean by that? So this is multiplication of a matrix by left. Okay. And let me also write down what is the matrix multiplication by right. So this equation, and then this is matrix multiplication by right. Okay, so I multiplied A inverse from the right hand side. So this is not same as, this is not same as this thing. So this equation is not same as this thing. So it
Sir,
is
can
not
you do with
like this. Yeah. Can I do with
sir,
what?
sir 3 cross 3 matrix, sir, Cramer's rule.
I have already discussed for 2 cross 2, right? This is where I discussed in this part. I started with Cramer's rule in 2 cross 2 matrix.
Sir, 3 cross 3, I will ask.
Yeah, but you can similarly generalize it for 3 cross 3 also. If I have time at the end, I will discuss that. I need to cover more material. Okay. So I will discuss if I have time
Okay,
at
sir.
the end.
Okay,
Okay.
sir.
Okay.
Okay.
Sir, one more question before we proceed. So you said determinant,
Yeah.
if it is equal to 0, then there is no solution. And if the
No,
determinant
no, no. If it is equal to 0, then it has infinite many solutions. I
infinitely
said,
many solution. Okay.
yeah,
And
yeah. Not if it is, yeah, yeah. If it is non-zero, then it has a unique solution, which you can obtain by this Cramer's rule.
okay. And actually we have three cases, right? No solution, uniquely many
Yeah, no
solution.
solution also. Yeah, yeah.
So where do we get no solution? Is equal to 0 or not is equal to 0?
In this case, you will always get a solution. It's just a matter of fact whether whether you will get infinite many solution or unique solution.
Okay. So
No solution makes sense when you have more equations and lesser variables. Then you may have some inconsistency with the solution. For example, let me give an example. Let's say you can have system like x plus y is equal to 1, x 2x plus 2y is equal to 2, and then x plus uh, yeah, and then let's say x plus y is equal to 3. Okay. So in this case, can you expect any solution? That is the point. So in this case,
Yes, sir.
I think you can expect, yes. In this case, you can expect, let me write it, is to be xy is equal to x to 0.
okay.
Right. Now, in this case, you cannot expect any solution.
Correct, sir. So actually, I saw a few
Right.
questions where they asked three cases, right? Infinitely many solution, no solution, and solution. So I was just
Right.
thinking, how do I identify the three things in the questions?
Right. How many equations, how many variables were there?
Well, I don't remember exactly, but they were asking whether it has got a unique solution, no solution, or infinitely many solution. So I distinctly remember there are 3 cases that they spoke about in the question.
Yeah, there are 3 cases. You can use determinant to find out that. So
Okay.
if it is, if the number of variables is equal to number of unknowns, right? So now let's come back to this. So we have a system of equation. So because we are working with number of equation equal to number of variables, so we have a coefficient matrix to be a square matrix, and then I can write down it in the matrix representation form like this. Now, because determinant, I'm assuming that determinant is also non-zero. Okay, so what I can do, I can use inverse of a matrix. Okay, I can use inverse of a matrix. I can use inverse of a matrix to find out the solution. Now, how do I use that? So I can multiply inverse of the matrix from the from the left hand side, and then I will get this equation. So now we know that inverse of the matrix, this thing is equal to identity matrix, In x bar, and this is I inverse B. So we will get it to be x bar right. So now let me first start with the definition of inverse of the matrix. Is it seems like it has not been thought of as of now. You have not seen this. If you don't know, if you do not recall it, so let me write down the definition. So in this case, you can. This is another way to find out the solution.
Sir, a question for you, sir. Sir, can we multiply like the same matrix both sides? Is it okay?
Yeah, you can do that.
Oh.
But then it will not give you anything. It will just, if you multiply the same matrix, you will get a square x is equal to ab. It doesn't help you, right, to find out the solution. So it is of no use. Right. Now, let us recall what is the inverse of the matrix. So in this, sorry.
So I would like to ask, sir, so here it says that if we want to find the x variables, just we can find the inverse of A and multiply it by B, and it should give us the answer, is it?
Yes.
Okay, okay, okay. Okay, thank you, sir.
So, but there were conditions. We are working with very specific type of system of equation. Now, what are the condition on that? Number of variables is equal to number of equation. Second condition is that determinant of the coefficient matrix is non-zero. In that case, we can have Cramer's rule that we discussed, and now we can also use this. So in today's rest of the lecture, I will give you a method to calculate the inverse of a matrix. Okay, given a square matrix, how do you calculate the inverse of it? All right. So yeah, so let us first recall what is the inverse of a matrix. So inverse of a square matrix n cross n. So and the inverse, inverse of matrix A is an square matrix, square n cross n. In particular, matrix says that a square matrix A inverse says that A inverse multiplied with A from the left is equal to identity, and A inverse multiplied with from the right is also equal to the identity. Okay. Okay. So now let's say, so we already know that if A is invertible, then determinant is non-zero. Why? Because of the property of determinant. Suppose uh, suppose determinant, suppose A is invertible, that means there exists an inverse. So that means it satisfies this inequality, this equality, right? So if I look at the determinant of this product by the product rule, it will be equal to determinant of A inverse times determinant of A. Now, okay, now what is determinant of I? So determinant of In is 1. It's a diagonal matrix. It is just multiplication of all the diagonal matrices. So now if you equate these two things, from using this equation, you equate these two things, what will you get? You will get determinant of A inverse into determinant of A is equal to 1, which will give you that determinant of A inverse is 1 over determinant of A.
Sir, this determinant inverse thing is the same as we did in with numbers, like multiplicative inverse or like that.
No, it's not same as numbers.
But the analogy we can relate it to that, right, sir?
Yeah, you can think of it in that way, but not too much because
Yeah.
it is not
Not
exactly like
exactly,
numbers.
exactly
Numbers,
like that,
let's
but
say a lot of
it's
properties we do not have in this case, so in matrices. But you can think of it in that way. Yeah. Yes. All right. So you can write down the determinant of the matrix also with respect to the identity. And this quantity itself tells you that determinant of A is not zero. Okay. Why? Because if a product of if you do a product, if you multiply zero with anything, it will give you zero. It cannot give you some non-zero number. So this also tells you that. So
yes,
this
sir. So none of them
thing,
can be zero, like not inverse, not zero zero.
yes, yes. So this also tells you that determinant of A is non-zero. So whenever you have a multiple matrix, then uh, it is same as to say that the determinant of A is non-zero. All right. Okay, but what about the converse part? So what do we mean by converse? Suppose you have determinant of A to be zero. Can you find out? Uh, so do we have A inverse or inverse of A? Inverse of A. All right. So that is what we are going to see today. So the answer is yes. Okay. So the answer is yes. And how do we find out the inverse of a matrix? So for that, we we calculate something which is called the adjoint of a matrix, and then using the adjoint of a matrix, or adjugate of the matrix, using the adjugate of the matrix, we will find out the uh, inverse of the matrix. Okay, so let me start with an example of 2 cross 2, and then we will write in generality. So let's say right. So we know that uh, given a matrix, let's say A11 up to A1n, AN1 up to N, n cross n matrix. All right, we can have cofactors associated with each entry. Okay, so Cij denote the cofactor of Aij. All right, and how it is defined? It is defined as -1 to the power I plus j, minor of Aij. And how do we calculate minor? It is determinant by removing I through and j through. So we already know all these things. Now, so using A, we calculate now because we are for each ijth entry we are finding out a cofactor. So we can form a cofactor matrix from this. So what is a cofactor matrix? Cofactor matrix of A is precisely the matrix which is obtained by the cofactors uh, of A. All right. So each entry So ijth entry of a cofactor matrix is basically Cij. And what is Cij? Cij is nothing but the cofactor of Aij entry. Okay. Now, so we call this matrix to be C. We define it to be C. C, why? Because it is cofactor matrix, so we call it to be C. So now let's look at an example. So let's take your matrix A to be a 3 cross 3 matrix. Okay, so this is a 3 cross 3 matrix. Now, what is the cofactor? So let me write down the cofactor of each entry in the respective place. So what is the cofactor of 3? Can anyone tell me cofactor of 3?
1.
And what about
Minus
cofactor of 1, 2? 1, 2th entry?
0.
Right. And what about 0th entry? Cofactor of
0.
0th entry, it is 0 again. And 0th, this 2 comma 1 cofactor
1.
is 1. Yes. Cofactor of 1 comma 1 is
3.
minus 3.
Minus.
No, no, it's not. No, it is minus 1 over here. Okay. So cofactor of 2 comma 1, it is basically minus 1 because we have minus 1 to the power 2 plus 1, which will give you minus 1 factor. And the determinant is 1. Now let's say it will be minus. Cofactor of 2 comma 2 is going to be 3. Cofactor of 2. What is the cofactor of 2? 0. What is cofactor of what is the cofactor of 3? 1. Cofactor of 3. Okay, let's see. Cofactor of 3 1 is
2.
2. All right. What is the cofactor of 3 2?
So minus 6.
Minus 6.
Right. What is cofactor of 3 3?
3, sir.
Yeah. Okay, so I have written down the cofactors in a matrix form. Right. So, so that means I have obtained a cofactor matrix. So C is the cofactor. All right. So now you know how to find out a cofactor matrix of a given matrix. All right. So this is not tough thing. So now let's say what is the adjugant matrix. So define the definition. The adjugate matrix of A is defined by is defined as adjugate of A is equal to C transpose. Okay. So in previous example, what is the adjugate matrix? Adjugate matrix of A in the previous example. Adjugate matrix was the cofactor transpose of the cofactor. So what was the cofactor? Cofactor matrix was this transpose of this. Now what is this? This is 1 0 0 minus 1 3 0. So row becomes column, column becomes row. That is what transpose is.
2, negative 6.
Right. Correct. So this is the code. This is the adjugate matrix of A. Okay. Now once you get the adjugate matrix, now you can find out the determinant also. Oh, sorry, the inverse of this. Now you can define inverse also. So let's define inverse. So we define A inverse to be 1 over determinant of A times the adjugate matrix of A. Okay, so scalar multiple of these adjugate matrix. So again, in the previous example, if I look at the previous example, if I look at the determinant of A, what is the determinant of A?
9.
It was, yes, it is 9. We can expand with respect to the first row. Is it 9? It is 3. It's not 9. Determinant of A, I'm 10. Okay, sorry. I've written the cofactor. So what is determinant of A? What is A? A is this, right? This is your A. This is your original matrix. You need to find out determinant of A,
3,
not the
3.
cofactor matrix. Yeah. So it is 3, 1, 0. So it is 3, 1, 0, 0, 1, 2, 0, 0, 1. So a separate triangular matrix.
Sir, we can also expand it along the first column, right? Or
Yeah, you can expand along first column. You will get the
so
same result. It doesn't matter. So you can expand along the first column or last row. You will get the same. So either way, you will get 3 as the answer. And now you plug all these values into this formula of the inverse, and you will obtain the inverse of the matrix. So A inverse will be 1 by 3 of this adjugate matrix, which is 1, minus 2, minus 1, 2, 0, 3, 6, minus 6, 0, 0, 2. Okay, so what does it mean? To divide everything by 3. It's 2 by 3, 0, 1, 2, 0, 0, 1. Okay, so this is your inverse.
So value 2 comma 3 would be minus 2 now.
Sorry, yeah. Yes. Yeah, I do these small typos, so please be attentive and let me know whenever you find one. Okay. Yeah, thanks for pointing out. All right. So you can also check that if you multiply this matrix. So if you want, we can do verification as well. Yeah, let's set up each. Right. So now let's verify also. So what was A? So verification means multiplying A inverse with A will give you identity on one. Okay, so what is A inverse? It is 1 by 3 minus 1 by 3, 2 by 3, 0, 1 minus 2, 0, 0, 1. Multiplying it with the original matrix, which was 1, which was 3, 1, 0, 0, 1, 2, 0, 0, 1. So what will be the first entry? What will multiply? First
yes,
row,
sir. So
first
2
column.
will be
Big one.
1, sir. 1.
Now what will be second entry?
0, right?
And what was the third entry? First row, third entry.
0. Minus 2 by
It
3
is minus 2 by 3 by
plus 2
3.
by 3. So
Right?
0
So it will be 0. Okay, now let's do second row, first column. Second row, first column will give you
1 by
0.
3.
No, 0. Second row, first column. Second row, first column. 0 multiplied with 3, 1 multiplied with 0, minus 2 multiplied with 0. Right? 0. You will get 0. What about the
second row
second entry?
1, sir. It will be 1.
Second row, second column? 1. Second row, third column?
0, I guess. Yeah.
Right. Third row, first column?
0.
Third row, second column.
0 again.
And third row, first column. Third row, third column.
1. Yeah, so
So this is
I will.
identity, right? And now also you need to verify about the other part. That if you multiply from the left also, from the right also, you will get identity. So I leave it up to you to check. So check this as well. Okay. So now we have find out how to calculate the inverse of a matrix. Okay. Of a square matrix, inverse of a square. So inverse only makes sense for the square matrices. All right. And I have already, and why I'm talking about the inverse of the matrix, because we can use these, we can use inverse to solve a system of equation which is of this particular type. In particular, the number of variables is equal to number of equation, and number of variables is equal to number of equation, and the determinant is non-zero. So in that case, you can also use inverse method to find out the solution of a given system of equation. All right. So, right. So now let me write down this thing in generality. Yeah. So in particular, you have a system of equation with coefficient matrix of non-zero determinant. So let's say you have this system of equation a11 x1 up to a1n xn equal to b1, a1 a21 x2 a21 x1 a22 x2 up to a2n xn is equal to b2, and so on. You have n many equations like this: n1 x1 an2 x2 ann xn is equal to bn. Right? Now you can also write it in the matrix representation form by writing the coefficient matrix which is of n cross n, and then a column vector of variables, and then column vector of the values on the right hand side. In particular, you have obtain an n cross n matrix, an n cross 1 matrix, which is equal to n cross 1 matrix. All right. Now, if determinant of A is non-zero, then you can either use Cramer's rule to find solution. So this is what we discussed earlier. Okay, find out solution x bar, or you can use inverse method, inverse of A. All right. You can also use inverse of A. And how do we calculate inverse of A? So inverse was defined. So first we defined the cofactor matrix, which is made of cofactors. Okay, it's called cofactor matrix. And then you define the adjugate matrix of A by dividing determinant and to the, sorry, by taking the transpose of the cofactor matrix. And then we define inverse by dividing the adjugate by the determinant. So these three steps we follow to find out the inverse. And once you have the inverse, you can find out the solution to the A inverse D bar. Okay, in this case, you just multiply your vector B with A inverse. Okay, so let me take up the same problem. Okay, that we had in that we discussed for Cramer's rule. Or okay, let's take a 3x3 problem, because that is what uh, you guys want me to discuss as well. So let's take a 3x3 system of linear equation. What do I mean by that? So let's say you have this system of linear equation. You have three variables: x, y, z is equal to 1, y plus z is equal to 4, and then 4x plus 3y plus 2z is equal to 0. And suppose you have this system of equation. All right. So what is the corresponding coefficient matrix? First of all, it is 1, 1, 1, 0, 1, 1, 4, 3, 2. What is x vector? Vector x is x, y, z. What is b vector? B vector is 1, 4, 0. All right. So in particular, you can also think of this as, you can also write this system as ax vector by is equal to b. All right, makes sense. Everything is fine. You guys are already familiar with all these things. Now, by Cramer's rule, let's first find out the determinant of it. Okay, to first of all check whether we can apply the inverse method or Cramer's rule on. So let's check determinant of A. What is the determinant of A? So we can expand using the first column, and then let's see. Is this correct?
Yes, sir. It is not 0. Determinant is not 0.
Yeah, it is not 0, right? So you can apply Cramer's rule also, or you can use the inverse method also to find out the solution. And it will have a unique solution because the determinant is non-zero, so it will always have a unique solution. All right.
Sir, do we use
So,
inverse to
yeah.
find solutions, or to find the inverse itself?
Yes, can you repeat?
So, sir, this thing we use for finding solutions through inverse, or we find inverse through this? Like,
No, no,
I
no.
for
We use
finding.
inverse. Inverse can be find out independently, right? I just told you by calculating the cofactor matrix and then adjugate matrix and then dividing it by the determinant, by scaling the adjugate matrix by determinant, 1
Yes,
over
sir. That
determinant.
part I got, sir.
The
That
inverse
like we can find inverse.
right. So inverse
I
can be calculated independently. You can use inverse to solve, to find out the solution of the system. Okay. So there are two methods that we discussed today. First is Cramer's rule. Another is the inverse, using inverse of a matrix. So Cramer's rule, if I want to use Cramer's rule, so what is AX? AX will be replacing my first column with 140. So 140, 113, sorry. Yeah, 140 is the solution. So 140, 113, 112. This is AX, AY, replacing the second column by 140. 104, 140, 112. What is AG? AG is replacing with respect to third column.
140.
Right? Now, what is AX? AX is determinant of A. What is
X
X?
upon
Determinant of A divided by determinant of A. Y is determinant of AY divided by determinant of A. Z is determinant of AZ divided by determinant of A. All right. Now you can solve this. I'm not going to compute this in full generality. Okay. So now let's take the
Just had
same
a
system
question.
of equation.
Sorry.
Yeah.
Yeah. So I just want to ask you, how did you calculate the determinant of matrix A? I mean, did you do a transpose of it first and then do a calculation?
No, expand along the column. You can do anything now. You can either expand along one column or you can expand along a row. It is independent of the fact. That's what we started with today's session, right? We
Okay. No,
realized that you can find out determinant using by expanding along any column or any row. It is independent of that fact, whichever you do.
Okay.
So
And
I
also you
just
started
I
with.
just take whichever row. Yeah.
Oh, okay.
Hmm.
Okay. All right.
You can do so. My preference for a computational purposes, I will always go for a row which has many zeros in. Okay, many zeros.
Okay.
So in this case, second row has 0 or first column has 0. Okay, so I will expand along any of these two. So that is what my preference. Okay, all right.
All right.
Right. So now let me take this same example of system of equation and work out the solution for in the case of this using the inverse method. All right. So let's take the same example. Let me take the same example um, and let's work out the details. All right. So A is given by this. Now, what is the, we have already seen the determinant of A is non-zero and it is in particular -1. The determinant of A is equal to -1. Now, what is the cofactor matrix? Cofactor matrix is, first we need to find out the cofactor matrix of A. So 1, it is 2 -1. For second I2th entries, for third it is, right, for 0th it is, for this, it is, right. So this is the cofactor matrix. You can do the computation later, you can check. So let me mark that, check. Okay. And now, what is the adjugate matrix of A? Adjugate is the transpose of C, which is all right. Now, what is the inverse of this? It is just multiplying with minus. So we will get 1, 1, 0, 4 minus 2, 1 minus 1, 0, minus 4, 2, 1, 4, 1, minus 1. All right. This is the inverse. Now, what is the solution? So solution of x bar is A inverse multiplied with B. So what is A inverse? We know A inverse is this. What is B? B know. B is 140. So what is the solution? It is 3 minus 3 minus 4 uh, minus 4 plus 4 and then it is 4 plus 4. What is this is the solution that we obtained? Okay, we didn't solve them. Okay. So this is what the solution is. All right. So you can verify whether you get the same solution by using the Cramer rule. All right. So this is an example. So this is how you can use this. Okay. Before we move on to what we are going to do next time, let me complete today's thing by discussing uh, quickly over this topic of homogeneous system of equation. Homogeneous system of equation. Okay. So what is the homogeneous system of equation? When your B vector is a zero vector. Okay. So what do I mean by that? Suppose you have a system of equation where the all the right on the right hand side it is zero. All linear equations are equating to zero. In particular, for an example, so for example, this is a system of linear equation, homogeneous system of equation. Or in generality, you will have like this equal to zero. All right. So this is a system. This is called homogeneous system of linear equation. Now, if the corresponding matrix, if coefficient matrix A is invertible, then you will always have a unique solution, which is zero solution. Then system AX equal to B bar has a unique solution, which is zero solution, which is, so X bar will be A inverse times B vector. Now B vector is always zero. So multiplication with zero vector of any type will always give you a zero vector in this. So it will always give you zero vector. In particular, this will be 0, 0, and many times. All right. So which is going to be 0 is going to be the unique solution. All right. So a determinant, so a homogeneous system of equation equation with an equation and variable as a unique solution if determinant of A is non-zero and has infinitely many solutions. If determinant is equal to 0. Okay. So now, in the next session, which is going to be on Thursday, we are going to look at the solution space of system of equation which are not of whose coefficient matrix is not a square matrix. Okay. For example, which has, let's say, for example, in this case, so it has three equations, but the number of variables are 4: x, y, z, and w. All right. So we will be looking at these system of equations, linear system of equations, where the number of variables, where it is non-square matrix you will obtain, and how to deal with them. Okay. So I hope, yes, Amol.
Sir, in the previous, could you repeat that, please? Homogeneous, show that homogeneous page. Sir, here, sir, is it, sir, here, so can we say this, that as we studied, that two lines, when they overlap, that has many,
Right.
infinitely many solutions.
Yeah, if they overlap, yeah, it is infinite many solution, right?
So this is this is what it is all about.
No, it is not, because when you say homogeneous system of equation, so your equation, it depends on the equation then.
Okay.
So if, let's say, if your lines are passing through origin, okay,
Yes, sir. Yes, sir.
in those cases, then it will have, then it is, then it what it means that it has infinite many solution. So, for example, so these two lines, so this is these two, the system correspond to a line, two lines
Yes,
in
sir.
R2, right?
Yes, sir.
And both of the lines passes through origin. Okay, so if line passes through origin, then whatever you're saying is correct. But in general, line may not pass through origin. They may not intersect origin. So in that case, you will not get a homogeneous system of equation. You will get some non-homogeneous. In particular, the constant values will not be 0. It will be some other constant. Okay.
Oh,
All right.
thank you, sir. Thank you, sir.
Yeah. So I think we should stop now, and
Sir,
we will meet.
question. I have a doubt, sir, regarding